Hi there. My name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is a video of Torsten Abel demonstrating the PPG Wave 2.3 synthesizer. And as an aside, if you're into synthesizers, you should really check out Torsten's channel because there's a lot of great stuff there. This is the datasheet for the SSM2044, which is a voltage-controlled filter chip used in the PPG Wave 2.3. This is the patent by Dave Rossum called Low-Pass Filter with Electronic Control of Cutoff and Resonance that's cited in the SSM2044 datasheet. And if we scroll down a little bit, we'll see that the very first figure in this patent is something called a Wilson current mirror. And such devices are the subject of this lecture. In recent lectures of ECE3400 analog electronics, we've been looking at various amplifier structures. In this lecture, we'll look at some building blocks that are useful in analog electronics that aren't voltage amplifiers per se, and we'll start with current mirrors built from bipolar junction transistors. So here's a basic current mirror consisting of two NPN transistors. The bases of the transistors are wired together, and the collector of Q1 is wired to the bases. IRF here is basically our input, so you can think of this as an independent source, but I'm in general not going to write the little circle here indicating that. We just sort of know by convention that that's our input. The output is indicated by I/O. And the name mirror comes from the fact that if you look at the arrows here, if we're pushing current into the mirror, we're also then pulling the equivalent current into the output. So you might think about a current buffer as taking current in and then pushing the same current out, but here we're flipping that around. So this sort of acts like a buffer for currents, but you have that arrow flip. Now, if you remember from our original lecture introducing the basic equations of the bipolar junction transistor, you'll remember that the saturation current and beta are both a function of the collector to emitter voltage according to the early effect. Now, if we were to neglect the early effect, then those collector currents are independent of the collector emitter voltage, and they're just a function of the base emitter voltages. Now, assuming that our transistors are matched, these will both have the same base emitter voltage, meaning they both have the same collector current. So the collector current for Q1 is going to match I/O, the collector current for Q2. Now, we can use our beta relationship and say that the base currents are then I/O divided by beta. And now I can say that the current flowing down into this junction of the bases, well, that's just twice the current flowing through any one of the bases. And now I can write a Kirchhoff's current law equation at this node. We have IRF going in is equal to I/O plus 2I/O over beta. I can then factor out I/O and divide both sides of the expression by this 1 plus 2 over beta term to get I/O equals IRF divided by 1 plus 2 over beta. Notice that as beta goes to infinity, this term here winds up going to 0, and you get I/O equal IRF. Now, this equation implies that I/O is going to be less than IRF. If you build one of these in lab, you'll occasionally find that I/O is actually bigger, and that's because of the early effect which we neglected. Now let's think about it in terms of a small signal output impedance computed looking into the output here. And that would just be little r IC, the resistance seen looking into the collector of Q2. And taking a look at Marshall Leach's BJT formula sheet for the Norton equivalent circuit looking into the collector, we see that one of the forms of RIC is this expression here. And notice there's an RTE. And if this RTE was 0, all of this stuff goes away and it just reduces to R0. And fortunately, if we look at the slide here, we see that there is no RTE down here. So the impedance looking into that node is just R0 for transistor 2, And I'm assuming that these transistors have the same characteristics, so I guess I could get rid of the 2 here, but I like to leave it in because that makes me happy. And remember that R naught is equal to VA, the early voltage, plus the collector to the emitter voltage for Q2 over our I naught. So I'm basically treating I naught here as a DC bias current. So we could model this circuit here as a Norton equivalent circuit, which is a current source I0 in parallel with this resistance RO2. Now remember that we computed this I0 by ignoring the early effect, but here we're including the early effect in this RO2, so this is really something of an approximate hybrid model. If you go to Marshall Leach's ECE3050 website, 3050 is an earlier number for 3400, and scroll down a little bit, you can find his notes on the BJT current mirror. And in these notes, he goes through a much more detailed analysis and computes an accurate formula for I0 using the Ebers-Moll model. I would encourage you to read that, but for our purposes here and for most practical purposes, this is a reasonable approximation. Now, one trick you might do to try to improve this formula is to replace this wire here with a common collector stage. So this trick is referred to as base current compensation, and we can analyze it much the same way. Once again, assuming that we have matched transistors, Q1 and Q2 have the same base to emitter voltage, hence they have the same collector current. So the collector current on the left here is I0, and then we can say that the current flowing through each base is I0 over beta. So the current flowing out of the emitter of Q3 is 2I0 over beta, and then I can say that the current flowing into the base of Q3 is 2I0 over beta times beta plus 1. And now I can write another Kirchhoff current law equation. So I have Iref equal to I naught, which is this I naught times 1, plus this 2 I naught over beta times beta plus 1, which is this term right here. And I basically already factored out I0 here. All right, so if I divide both sides by this mess over here, I can say that I0 equal Iref divided by 1 plus 2 over beta times beta plus 1. Now, the thing to notice here is that in the original 2-transistor current mirror, this extra term here that we're adding to 1 drops as 1 over beta, whereas this term here drops as 1 over beta squared. It's once again reasonable to approximate the output here using a Norton equivalent circuit using an I naught that we computed without taking the early effect into account, along with the RO2, a parallel resistance that comes from the early effect. And once again, you can look at Marshall Leach's notes if you would like a more accurate formula for I0. In both the original 2-transistor current mirror that we looked at and the 3-transistor current mirror that we just looked at, you can improve the output impedance by adding some resistances in series with the emitters. And people will do this on discrete designs on a PCB, but this generally is not the preferred approach for an integrated circuit, because integrated circuit design kind of flips around all of your intuition from PCB design. On a PCB, the resistors are relatively cheap compared to the transistors, but on a chip, the transistors are basically free and the resistors are fairly complicated. They're bulky and it's difficult to control the resistances precisely in a matched way. So on a chip, a preferred approach is to take this connection here and flip it around and then add a transistor up here, and this forms something called a Wilson current mirror. And this is that figure 1 from the patent associated with the SSM2044 filter chip I showed you earlier. Okay, so if the collector current of Q3 is I0, the base current is I0 divided by beta, and the emitter current is I0 divided by alpha. Now, if you look at the circuit down here, This looks like the original 2-transistor current mirror we had, just flipped horizontally. So if I remember this division by 1 plus 2 over beta from earlier, I can treat this I/O over alpha as the input of a 2-transistor current mirror and say that the output of it here is I/O over alpha divided by that 1 plus 2 over beta factor. All right. We can again write a Kirchhoff current law equation for this node associated with IREF and say IREF is equal to I/O over alpha times 1 plus 2 over beta plus this I/O over beta. So let me first replace alpha with beta over beta plus 1. All right, so multiplying through by beta over beta plus 1, I wind up with beta over beta plus 1 in this spot here. And then when I multiply beta over beta plus 1 times this second term here, the betas wind up canceling, so I wind up with 2 over beta plus 1. So I can combine these terms and wind up with 1 over beta plus 2 over beta plus 1 over beta. All right, so let me simplify this fraction here by multiplying the numerator and the denominator by beta plus 1, which yields this expression here. So dividing both sides of the expression by this quantity with all of the betas, I wind up with I/O equal IREF divided by beta plus 1 over beta plus 2 plus 1 over beta. And again, thinking about what this looks like as beta goes to infinity, well, this second term here winds up going away, and this term here winds up going to 1. The main advantage of a Wilson current mirror is that it has excellent output impedance. And since the output here is a current source, by excellent, I mean it has a very high output impedance. So to compute the output impedance, I want to think about IREF here as being a current source. And let's assume it's a non-ideal current source. So I might put a resistance RF in parallel with it to indicate its potentially non-ideal nature. So I could put a little ground up here. All right. Now when computing a equivalent resistance looking into the output here, remember I'm computing a small signal quantity. So I would basically zero out this current source. So I would open it up, leaving me with just this resistor. And I would turn these V minuses into grounds. So that's what I do on the next slide here. Another thing I'm doing that's a little bit weird is notice this Q3 is now a Q3 prime because I'm using this resistor here, RO3, to indicate the raw output resistance of Q3. So this entire thing here is really the full Q3. And Q3 prime is sort of an ideal transistor that doesn't have that effect. All right, notice that I haven't put an RO2 and an RO1 in here because really the early effect on Q3 that gives you this RO3, that's really the only early effect that's significant in the results that we want to compute. So I'm not worrying about the early effect for Q1 or Q2. Again, remember in the original circuit, we had our input source IRF here, but this winds up getting zeroed out when we're considering the small signal circuit to compute an output impedance, so you don't see that here. So to compute the output impedance looking into the collector of Q3 here, I could either fix the voltage at the output with an independent voltage source, compute the resulting current, and divide those quantities, or I could do what I'm actually showing here, which is I fix the current flowing into the collector using an independent current source, compute the resulting voltage, and then compute the output impedance by dividing the test voltage by the test current. Now, technically, you could use either approach. I've generally found that for circuits like this, using a current source to drive the circuit is usually more illuminating. Your mileage may vary. Now, to actually compute what R-out is using small signal models for the transistors turns into a big, massive mess. You wind up with this tangle of simultaneous equations that you need to solve. So I'm not actually going to compute R-out here. what I'm going to do is present a not entirely satisfying, highly hand-waving argument to justify why this improves the output impedance. And remember, here we think of an improved output impedance as being a higher impedance because we're thinking about the output here as a current source. If it was a voltage source, we would want a low output impedance. All right, so here's the general idea. So I'm forcing a current I test into the collector of Q3 here. So it can go down this direction into essentially the controlled current source, or it can go down through RO3. Now, the current here is actually being controlled by the base to emitter voltage. So this current isn't going to change unless something changes that base emitter voltage. The way to think about this is that we'll now imagine, okay, well, this test current is essentially wanting to drive a current through RO3. And by driving a current this way, we can imagine that it's increasing the voltage here because we know that pushing current into a node makes the voltage go higher. And that is making a current kind of flow down this direction. So we're imagining that the voltage here is going up. So the voltage here is going up because this is all the same node. And now if I think about Q1 as a common emitter amplifier, remember that has an inverting amplification effect on the voltage. So if the voltage goes up here, it goes down here. And now going into the base of Q3, well, this is acting like another common emitter amplifier, so we get another inversion. So the voltage going down over here on the left means that we have the voltage going up here. So we basically have a positive feedback loop that is increasing this voltage and increasing our out. A little bit later in the class, when we look at feedback amplifiers, we'll do a lot of this kind of hand-waving analysis of seeing what goes up and what goes down. Now, there's another positive feedback loop here. If we imagine that the voltage going up here corresponds to the voltage going up here, well, Q3 is sort of operating as a common base amplifier, and that has a non-inverting amplification effect. So that would also make the voltage go up here. So I basically have two positive feedback loops increasing this voltage and hence increasing our impedance. If that made your head spin a bit, that's okay. It makes my head spin too, but that's the argument Marshall makes in his write-up, and it seems reasonable. So all of the mirrors we've looked at so far have involved NPN transistors. So they take an incoming reference current and create an incoming output current. All of the mirrors we've looked at so far have complementary PNP versions. And so for these, you essentially have some sort of current sink that is pulling current out of the mirror to provide the reference. And then there's a current being pushed out of the output. And so for the PNP versions, you reverse the directions of all the arrows and you flip the role of V plus and V minus. And I'll also mention that when people talk about current sources, sometimes they try to be more precise in terms of reflecting its role in the circuit. In this case, because we're pulling current out of the mirror, you might think of this as a current sink. So you'll hear people use that terminology, and they'll refer to a source like this as a current source to distinguish it from a sink. But of course, current sinks and current sources in this more limited sense, they are both current sources. It's just a matter of how you're using them that indicates whether somebody might want to make the distinction between source and sink. Your mileage may vary. This is the Buchla 259 programmable complex waveform generator. If you take a look at the fairly frightening schematics of the Buchla 259, you'll see the example of a current mirror formed of PNP transistors. That's this Q6 here. And notice that there are some resistors at the emitters. And the current mirror is set on top of a differential pair. This forms a fairly primitive version of a circuit called an operational transconductance amplifier. Marshall Leach discusses operational transconductance amplifiers in his notes on current mirrors, and he shows the schematic of a much more sophisticated operational transconductance amplifier. Such amplifiers are also called OTAs, and they're kind of like regular operational amplifiers, except that you have 3 inputs instead of 2. You have 2 voltage inputs like with a regular operational amplifier, but you have a third input that controls the tail current on the differential amplifier, and it basically lets you control the gain of the amplifier. So instead of having a fixed, fairly large gain like on a standard op-amp, you get to control the gain. The other difference is that an operational amplifier is thought of as a voltage output device, whereas an OTA is a current output device. The ability to control the gain of the amp with this third input makes it extremely useful in designing analog synthesizer circuits. And in fact, if you take a look at my analog circuits for music synthesis class, about half of it is basically an extended discussion on applications of the OTA. So I'm not actually going to talk about OTAs further. If you're personally interested in learning about them, you should check out this lecture from my Analog Circuits for Music Synthesis class, where I show how to use an OTA to make a voltage-controlled amplifier, and a couple of the lectures after that, where I look at some specific examples of such circuits. And I'll also mention that one of the lectures in that class focuses on voltage-controlled oscillators like the Buchla 259.